Thank you so much. You all seem so far away. Folks, I'm going to share my struggle with you. I lost my voice 10 days ago, and somehow it was this crazy bug. I don't know if you can hear it. It's still, I can still hear it in my own voice. So in case my voice goes out in the middle of this talk, I have a plan. I'm going to switch to a charades format, so I'm going to need your help to interpret what the rest of my slides say. But my name is Paul. My amazing co-author is Nitin Kohli. And this talk is about a particular type of data format. It's something called a table of counts. So this is a table of counts. And on the left, you can see we have a list of names of different categories. So these categories, they could be states, they could be countries, they could be sessions inside of a conference. And on the right side, we have counts of people. So in each row, we have the number of human individuals that belong to a particular category. So of course, tables like this are actually pretty common. And if you have data in a format like this, you might be interested in privatizing it. I mean, especially if you're here, but hopefully otherwise too. So how do you privatize a table of counts? Well, if you look at the literature, the available algorithms look pretty much like this. You take each row, you add an independent noise random variable. And then at the end, of course, you can post-process your results. So for example, you might take all of the negative values and set them equal to 0. And how do you evaluate a system like this? Well, so far in the literature, the focus is on what I want to call accuracy of counts. And so all I really mean by that is that we look at one of these counts and we consider what's the typical distance between the true count and the published output count. Most often, this is just mean squared error in most papers. But how does that relate to the way that people actually use these tables of counts? Well, if you look at different research papers, I'd say there are at least two types of questions that you could try to answer using a table of counts. The first type is something called a category-based question. So how many people live in Alberta? So this is a question that uses the name of at least one category, and really you have to perform a lookup using this name. But there's actually other types of questions out there, and I have some examples here. And by the way, these are examples that my co-author and I found by Googling different research papers. So what fraction of US flights have 0 air marshals on board? What fraction of company boards have more than 2 women? What is the average number of students overseen by each guidance counselor in the US? So what all of these questions have in common is you don't need the names of any categories to answer them. Actually, you could take that first column, the column of names, and just delete it, and only work with the column of counts. Now let me give you a new way to think about that column of counts. I could take all those count values, and I could plot them on a histogram. Okay, so in this histogram, in position I, we have represented the number of states, or some other category, that has exactly I people inside. So of course, I'm not saying that you would necessarily create this histogram as part of your analysis, but just that this is a representation of statistical information, information that we need if we want to get good answers to these count distribution questions. And so this suggests to us a different type of performance criterion. It's something we call accuracy of distribution. So unlike accuracy of counts, accuracy of distribution asks, well, what's the difference in this distribution of counts that we get as a result of privatization? But now we get to a problem. So the big problem is that if you look at all the available differentially private algorithms that are out there, they all distort this distribution of counts. So I'll give you one example. Some of you may be familiar with the truncated geometric mechanism. If you apply that mechanism, you'll tend to get an inflated number of zeros in your data set. So that's just one example. So our goal in this work became to design privatization methods that preserve this distribution of counts. But really, we want a privatized table that's useful for more than just one kind of user. So if you think about it, what I really mean is that we want to balance 3 different types of performance. So we have our new criterion, as accuracy of distribution. we still want to pay attention to accuracy of counts, and we have to pay at least a little attention to runtime because, of course, we want our algorithm to finish sometime this year. So now let me give you just a little hint about how we attack this problem. So you can take any of these count mechanisms, at least any count mechanism that applies independent noise to each row. And you can represent it as a transition matrix, like this transition matrix T. So the way to understand this is the row corresponds to the true, the input count. The column corresponds to a potential output count. So choose a number in there, and if your number is at row I and column J, what that means is if the true count is I, what's the conditional probability that you get an output count of J? And now let's take our true distribution of counts, and let's arrange it into a row vector, and let's call that row vector Z. And then we're going to take that distribution, we're going to apply this count mechanism. And if you think about the way that matrices work, it turns out that the expected distribution of your outputs will be the product. So Z times T. And so we can say that Z is a fixed point if those two are equal. So Z equals Z times T. And also we'll let f of Z be the set of all of these count mechanisms T that are both differentially private and also have this fixed point Z. So I hope you agree this sounds promising at this point, right? These are at least good candidate mechanisms that we might want to choose from when we're designing our system. But there's one extra problem at this point. So the problem is, of course, that the true distribution of counts has private information. And so if we just set Z here equal to the true distribution of counts, we could accidentally leak that information and break the differential privacy guarantee. So instead of that, we need to use a two-stage framework. So in the first stage, you take that true distribution of counts and you privatize it with something we're going to call a distribution privatizer. It's going to be labeled D here. And that gives us a privatized version, which we'll label Z. And then in the second stage, we'll take Z and we'll pass it into something we call a constructor algorithm. And it's labeled C here. So it's the job of the constructor to choose the actual transition probabilities in that count mechanism T. And then finally, you can take each row of your table of counts, process it through your count mechanism, and that gives us the privatized table of counts. So we actually did work on pretty much every part of this two-stage framework. But for this quick talk, I just want to zero in for a moment and tell you a little bit more about that constructor algorithm. So remember, it's the job of this constructor to choose those transition probabilities in T. And early on, we had this idea. We thought, okay, we want this constructor to look inside this set, this promising set, f of Z. And additionally, we wanted to choose the mechanism in that set that optimizes accuracy of counts. So our thinking was, we already have this fixed point constraint, and the fixed point constraint supports our goal of accuracy of distribution. And so if additionally we work in accuracy of counts, hopefully we'll get a good balance between the performance criteria at the end. Now it turns out that this set, this f of Z, is what we call a convex polytope. So a polytope is an intersection of linear half spaces. So here in 3 dimensions, I have some examples. So these are polytopes, examples of polytopes in 3 dimensions. In this work, we're talking about a much, much higher number of dimensions. So unfortunately, it turns out that standard optimization algorithms, they just run way, way too slowly to be able to perform an optimization over these polytopes. And another kind of obstacle for us is that there's really not any existing theory about these mechanisms that could help us design faster mechanisms. And so in response, my co-author and I, well, basically we did a whole bunch of linear algebra. And what we're able to do is to rewrite mechanisms, this promising set of mechanisms in f of Z in terms of simpler building blocks. And the simple building blocks are things we call epsilon scales. So an epsilon scale is a probability vector. It's in a column. And when you step down from one probability to the next probability, it's always a step up, a small step up by e to the epsilon, or a small step down by e to the epsilon. And so, think about this as walking up and down stairs. And we have a result that says that all of these mechanisms in f of z can be written as a conic combination of these scales, these epsilon scales. And so we can do things. We can take this theory and we're actually able to design new constructor algorithms that build up transition matrices one scale at a time. And these can run much, much faster than those standard optimizers. So let me zoom back out for a moment. I think that's my time. I'll just say we've done a whole lot of other things in this paper. So we have a new distribution privatizer. We have more to this mathematical theory. We have new constructor algorithms. And then finally, we have a set of experiments where we take real data and we privatize it using different methods. And just to highlight, we do in fact have some good positive news from those experiments. So there's some scenarios, some data sets, and some situations in which our two-stage framework has, I think, really good results. So we have sometimes significant improvements in accuracy of distribution. Accuracy of counts can remain close to the optimal level, and runtime is reasonable. So I hope at the end I've convinced you all that accuracy of distribution is an interesting sort of performance metric that you might want to study. And yeah, I'd love to talk more with you at the poster session. Thank you.